Okay, well, welcome to lecture 30. So before we get into the material we want to cover today, I just wanted to summarize the three cases that we worked on in the last two classes. So we were solving homogeneous systems of linear ODEs here in this matrix form, x prime equals a times x. And recall there were three different cases that we looked at where we found the eigenvalues of this coefficient matrix A. And in case one, if we found distinct real eigenvalues, then we had one solution. Case two, we had repeated eigenvalues, and the solution depended on whether we could find a complete set of eigenvectors or not. Okay, so if we couldn't find a complete set of eigenvectors, we had this extra equation that we had to solve here, and that would change the second solution x2. And then in the case of complex eigenvalues, then we had a third type of solution. Okay, so where we took the real and the imaginary parts of the eigenvalues and the eigenvectors, and then had our two linearly independent solutions of this form here. So I just wanted to put case one, case two, and case three summary all together, all in one place. So you've got case one, case two, and case three. And my suggestion to you would be maybe to save those slides or print those three slides out and have them at your side when you're solving these kind of problems. So there's a 3-slide summary there of what we did in the last two classes. So today we are going to be turning higher order ODEs, so a singular ODE, singular higher order ODE, into a system of ODEs, okay? And that is going to allow us to use these matrix techniques that we've learned to solve these higher order ODEs. And then we're also going to be looking at non-homogeneous systems of linear ODEs with constant coefficients. And so we have already solved one non-homogeneous system, but we're going to look at perhaps some more slightly complicated examples today. Okay, so an nth order ODE can be written as a system of, in fact, n first order ODEs. So that is my claim. So let's have a look. How does that work? So for example, here I have one ODE. I have a second order linear homogeneous ODE. So the second derivative of y with respect to t minus y equals 0. Or equivalently, I actually prefer the prime notation. So y double prime minus y equals 0. So my claim is that I can turn this single second order linear homogeneous ODE into a system of two first order ODEs. Okay, and how am I going to do that? Well, I'm going to introduce a new variable, x1, and the definition of this variable is going to be x1 equals the derivative of y. Okay, so I'm going to keep y as a dependent variable, but I'm going to introduce a new dependent variable called x1, which is the derivative of y. And so you can already see now that I actually already have a first order ODE, linear ODE for y. Y prime is equal to x1. That's a first order ODE. Okay, but if we have two dependent variables, x1 and y, we want two first order ODEs for these variables. So we have one first order ODE here, but we need a second first order ODE, and in particular we need a first order ODE for x1. So what I'm going to do is I'm going to differentiate x1. So x1 prime, if I differentiate x1, I get y prime. If I differentiate y prime, I get y double prime. So x1 prime equals the second derivative of y. Okay, but if I look at my original ODE, y double prime minus y equals 0, effectively what I'm saying there, I can replace y double prime in this original ODE with x1 prime. Okay, so if I do that, I can write my original ODE as x1 prime minus y equals 0. Because of my original ODE, y double prime, I've said here that y double prime equals x1 prime. So therefore I can write x1 is equal to y. They're very simple. So now I have a first order ODE for y here, y prime equals x1, and a first order ODE for x1, x1 prime equals y. Okay, so I'm going to combine these two equations now into a system of first order ODEs. Okay, so now I have a system of first order ODEs, two linear, in fact, first order ODEs. I'm going to let x equal my dependent variable vector be x1 and y, so my two dependent variables there. A is going to be the coefficient matrix. So again, the first row of A is the first equation. The second row of A is the second equation. The first column of A represents the coefficients of the first dependent variable. So that is the first entry in X, which is x1. The second column of A represents the second dependent variable, so y. So if I look here, my first equation, we have 0x1, so 0, but 1y, so 1, so 0, 1 in the first row. In the second equation, I have 1x1, but 0y, so 1x1 and 0y's in the second row of the A matrix. So therefore, this second order ODE can be written as a system of first order linear ODEs in matrix form. So what I've done is I've taken the second order ODE, which of course I can solve using other methods, and I've written it as a system of two first order linear ODEs, which I can solve using the methods from the previous class. Okay, well, let's try a higher order example now. So I've got a third order ODE here, and so I want to turn this into a system of three first order ODEs. So I'm going to start in the same way as in the previous example. I'm going to introduce a new variable, x1 equals y prime. Okay, so again, I've already found a my first order linear ODE here, y prime equals x1. And now I want to introduce a second new variable, which is the derivative of our first new variable. So x2 is going to be equal to x1 prime. So now you can see I have a second first order linear ODE for x1. x1 prime equals x2. And of course, because I've got three dependent variables now, y, x1, and x2, I want a differential equation, in fact, a first order differential equation for x2, so I should take its derivative. So x2 prime, well, if I take that derivative, x2 prime equals the derivative of x1 prime, so x1 double prime. Okay. But x1 equals y prime, right? So the second derivative of x1, if I take two derivatives of x1, here I get x1 double prime. If I take two derivatives of y prime, I'm going to get y prime prime prime. So the third derivative of y. Okay, and then using the original ODE, I can see that y triple prime is going to be equal to negative 2y prime negative 1. Okay, so y triple prime, just rearranging that original ODE, y triple prime is equal to negative 2 times y prime minus 1. Okay, so really what I'm saying here is I can rearrange y triple prime simply like so, but y prime, actually what y prime is, I said that y prime is equal to x1. So I can write, whenever I see a y prime in this equation, I can write it x1. So y triple prime is equal to negative 2 times x1 minus 1. And so really what I'm saying is that x2 prime, which is equal to y triple prime, so x2 prime is equal to negative 2x1 minus 1. So now I have three first order linear ODEs for my three dependent variables. Y prime equals x1, x1 prime equals x2, x2 prime equals negative 2 times x1 minus 1. Okay, so I can put those all together, those equations all together, and I can, in fact, I'm going to rewrite them over here. So I just want to point out that this third order system of first order ODEs, I don't know, that's worded kind of strange. This system of three first order ODEs are non-homogeneous, in fact, because they got this negative 1 term. But I can write these in any order that I want to. As long as I'm consistent, I can see I've written them here in the order x1, x2, and y. rearrange the order, it doesn't matter. As long as you're consistent when you're defining your vector x. Okay, so my dependent variables x, I've written them as x1 because that's the first equation, x2 because that's the second equation, and y because that's the third ODE. And of course, I have to therefore also be consistent with my coefficient matrix A. So the first row of A corresponds to the first equation, the second row of A corresponds to the second equation, and the third row of A corresponds to the third equation here. The first column of A corresponds to the first variable x1, the second column of A x2, and the third column of A y. So looking at my equations here, my first equation has 0 x1s, 1 x2, and 0 y, so 0, 1, 0. My second equation has negative 2 x1s, 0 x2s, and 0 y, so negative 2, 0, 0, and so on. And of course, I have this non-homogeneous term here. There are no homogeneous terms in the first or third equations, but I have a non-homogeneous term in the second equation, so I can write my non-homogeneous vector as 0, negative 1, 0. And therefore, I can write my third order non-homogeneous ODE, single ODE, as a system of 3 first order ODEs. And then I can solve this system, written in matrix form here, using these matrix methods that we learned in the last 2 classes by finding the eigenvalues and eigenvectors of this coefficient matrix A, and then also finding a particular solution using the method of undetermined coefficients. Okay, well, let's look at one more example here. Again, a third order ODE, but a slightly more complicated one because we have a third derivative plus a second derivative plus 2 times a first derivative minus 3 times y equals 0. But we're going to approach this in the same way. We're going to introduce 2 new variables. So x1 equals y prime, so there's my first order ODE. x2 equals x1 prime, so there's my second first order ODE. Okay, but x1 prime, if I take the derivative of x1, I'm actually going to get y double prime. Okay, so x2 equals y double prime. Well, I want an ODE for x2, so I'm going to take the derivative of x2. So x2 prime is equal to y triple prime. And now, of course, I can use my original ODE to find an expression for y triple prime. So if I rearrange this original ODE, I find y triple prime is equal to negative y double prime, negative 2 times y prime, plus 3 times y. So this is just the definition of this third derivative of y from the original ODE. Okay, but y double prime, I've already said that it's equal to x2, right? So x2 equals y double prime. So this is actually negative x2. Y prime, I've already said that is equal to x1. So this second term here is actually negative 2 times x1. And well, y is a dependent variable, so I can leave that as it is. So I can write x2 prime is equal to negative x2 minus 2x1 plus 3y. Therefore, I can write my 3 first order linear ODEs as y prime equals x1, so from this first equation here, x1 prime equals x2, and x2 prime equals negative x2 minus 2x1 plus 3. Okay, so recall here I've written y as the first equation, x1 is the second, and x2 is the third, so I've written my variables in that order as well. So my y terms, my x1 terms, and my x2 terms, because I think that makes it really easy to read off the coefficient matrix A if you do it in that way. So I've added the 0 terms in here as well. Okay, so there's no y terms in this first equation, but I've added it in because I feel like it's easier to read that way when we're writing it in matrix form. And again, the order of my variables didn't matter, so here I've written y first, then x1, and then x2. It doesn't matter as long as I'm consistent. So my vector of dependent variables is y, x1, x2. And my matrix is going to be, well, the first column here is related to the y variable, because that's the first variable. So 0, 0, 3. My second column is related to the x1 variable, because that's my second variable. So 1, 0, negative 2. And my third variable is x2, so 0, 1, negative 1, 0, 1, negative 1. So I can write my third order linear homogeneous ODE in this matrix form, which can be solved using the methods from the previous class. I have to find the eigenvalues and the eigenvectors of this matrix A, and then decide whether I'm in case 1, case 2, or case 3, and I can immediately write down my general solution. Okay, so you are expected to know how to turn an nth order ODE into a system of ODEs. Okay, so this is a skill that I am asking you to practice, and of course we'll practice in the workshop as well. And there are examples in the book, textbook, and the study guide. Okay, so previously we have actually solved a non-homogeneous system of linear ODEs with constant coefficients. But I wanted to give you a few more examples of that. Okay, because previously we only solved the case where f, the non-homogeneous vector, was made up of constants. Okay, so just as a reminder, the general solution to the non-homogeneous system of linear ODEs is given by the sum of a complementary solution vector plus a particular solution vector. And again, just as a method of recalling, the complementary solution vector is associated with the associated homogeneous equation. So we just solve this first part, x prime equals a times x, okay? And that gives us a complementary solution by finding the eigenvalues and the eigenvectors of matrix A, and then determining whether we're in case 1, case 2, or case 3. Okay, and xp is a particular solution vector which we can find using the method of undetermined coefficients. Okay, so, well, maybe we can just go through one example of a constant non-homogeneous vector where f is equal to some constant. So we have an initial value problem here. It's a second order linear initial value problem. So we have y double prime minus y equals 1 with two initial conditions. So what I'm going to do is I'm going to let x1 equal y prime, and therefore x1 prime, if I take the derivative of this equation, x1 prime is equal to y double prime. Okay, but from the definition of the ODE, y double prime is equal to 1 plus y. Okay, so x1 prime is equal to 1 plus y. Okay, well that's where that comes from. So my variable, vector of variables is dependent variables is x1 and y. Okay, so therefore my coefficient matrix A, the first equation is x1, or first dependent variable is x1. So x1 prime, well, there's no x1s here, and there is one y, so 0, 1. The second equation here is associated with y, so I get y prime is equal to 1x1 and 0y, so 1, 0. But I also have some non-homogeneous terms. So in this first equation, x1 prime, I have a plus 1. So f is equal to 1, 0. But notice here we also have some initial conditions, right? We have the initial conditions y0 equals 0. Okay, so well, y is one of our dependent variables, so this one can stay as it is. But this second initial condition must change. Because y prime of 0, we don't have a y prime anymore. We have this new variable, x1. Remember, we've only got first order ODEs now. We've got two first order ODEs. But that's okay, because x1 is equal to y prime. So really what this is saying is when t equals 0, y prime equals 1, or when t equals 0, x1 equals 1. So I can write my initial conditions as y0 equals 0, when t equals 0, y equals 0, as before. When t equals 0, x1, this should be, equals 1. So there we go, I fixed that. So when t equals 0, x1 equals 1. Oh, and I did it on that one too. So let me fix that one too. Okay, so I can write my my two initial conditions in terms of the vector of dependent variables. Okay, so x0 is equal to 1, 0, because x1 is the first dependent variable in this x vector, y is the second. So x1, the initial condition on x1 is 1. So that's first because it's the first variable in X. And the initial condition on Y, which is the second variable, is 0. Okay, so there are a few subtle things about writing systems in matrix form, and so I'm hoping that you're following that along. Okay, so now to solve this system of ODEs, I'm first going to solve the homogeneous version to find the complementary solution vector. So this matrix here, it should be pretty easy for you to find the eigenvalues and the eigenvectors of this matrix. But what you should find is that lambda 1 equals 1 with associated eigenvector 1, 1. Lambda 2 equals negative 1, so the second eigenvalue is negative 1, with associated eigenvector negative 1, 1. So please go away and make sure that you get the same results that I do when you find the eigenvalues and eigenvectors of A. Okay, so therefore the complementary solution is equal to the linear combination of these. Okay, so C1 times e to the t, so 1 times t is associated with lambda 1 equals 1. The eigenvector 1, 1 is associated with lambda 1 equals 1, plus C2 times e to the negative t, so the eigenvalue of negative 1, and the associated eigenvector is negative 1, 1. So our complementary solution, this was of course case 1 because we had distinct real eigenvalues. So we have our complementary solution. Now we need to find our particular solution. So again, this is quite a simple case because f is just a constant vector. So we're going to define our xp, our particular solution, as being two constants, a and b, which of course when we differentiate xp with respect to t, xp prime is equal to 0, 0 because a and b are constants. So if I use these two relations in my original ODE, x prime equals ax plus f, I get xp prime is equal to 0, 0 equals a times xp plus f. Okay, and if I read the system line by line, well, I get 0 times a plus 1 times b plus 1 equals 0. So I get b plus 1 equals 0. In the second line, I get 1 times a plus 1 times b plus 0 equals 0. So a plus b equals 0. So therefore b equals b equals negative 1, and a must equal 0. So my particular solution is going to be 0, negative 1. So now I have my complementary solution vector and my particular solution vector. I therefore just sum those two to find the general solution to the ODE. I can find C1 and C2 using the initial conditions. So when t equals 0, x should be 1, 0. So when t equals 0, e to the t becomes 1, and e to the negative t becomes 1. So I end up with C1 times the vector 1, 1, plus C2 times the vector negative 1, 1, plus 0, negative 1 equals 1, 0. So reading this line by line, 1 times C1 plus negative 1 times C2 plus 0 equals 1. So C1 minus C2 equals 1. And then the second line, C1 times 1 plus C2 times 1 minus 1 equals 0. And we should be able to find that C1 equals 1 and C2 equals 0 there. So the solution to the initial value problem using C1 equals 1 and C2 equals 0 is therefore e to the t times 1, 1 plus 0, negative 1. Because C2 was 0. Okay, so that's quite an easy example because our non-homogeneous term was just a constant. But what happens if now we have a polynomial? So in this case, just a first order polynomial as our non-homogeneous term. So f here is 2t negative 4t. Okay, so f is a linear function now. Okay, so step 1 is finding the complementary solution. Again, I'm going to leave this as an exercise because you should be able to find the eigenvalues and eigenvectors of this coefficient matrix fairly simply. It turns out that they are real and distinct eigenvalues. So we have a fairly simple complementary solution here. But what we're focusing on here is using the method of undetermined coefficients to find a particular solution. So what we're going to do is we're going to choose a particular solution of the same form as the non-homogeneous term. Okay, so this is a polynomial of order 1 in both of these terms here. So that what I'm going to do is I'm going to say my particular solution, or my test particular solution, is just a polynomial of order 1 in both of these terms. So a1 times t plus b1, a2 times t plus b2. Remembering that if we have a first order polynomial, we must also include the 0th order term. So, and for example, if we had a squared, so a t squared here, so a second order polynomial, I would have include all the terms in the second order test solution. Okay, well I want to use this in the ODE up here, so I better take its derivative. And again, the derivative here is quite easy to calculate because a1 times t plus b1, if I take that derivative, it's just a1, and similar for a2. Okay, so now using xp and xp prime in the original matrix form of the ODE, so xp prime and a times xp plus f here, I get this system of equations here. So xp prime is a1, a2 over here, equals a times xp, so this vector xp, so we have a matrix multiplication here, plus f, which f is the non-homogeneous term, t times 2, negative 4. Okay, so I can write out each of these lines of this, these equations individually. So the first line, for example, says a1 equals 1 times a1 times t plus b1 plus 2 times a2t plus b2 plus 2 times t. And similarly, the second line says a2 equals 3 times a1t plus b1 plus 2 times a2t plus b2 minus 4t. Okay, so here I have a system of two equations with 4 unknowns. So I've got a problem here, right? Because if I want to solve a system with 4 unknowns, I should have 4 equations. But notice that I have some of these terms in these equations are constants, like a1, b1, and 2 times b2, and some of them are multiplied by t, so a1 times t, plus 2 times a2 times t, plus 2 times t here. So what I can do is I can separate out the constant terms in each equation and separate out the t terms in each equation. So for example, in this first equation here, maybe I'll take a1 to the other side, so I have 0 is equal to minus a1 plus b1 plus 2 times b2. 0 is equal to minus a1 plus b1 plus 2 times b2. The second equation, again, if I take that to the other side, I get 0 is equal to minus a2 plus 3 times b1 plus 2 times b2. And so now I have two equations which represent the fact that the constants on either side of the equation must be equal. I can do the same thing for the t terms. So in the first equation, I have, if I take the 2t to the other side, I have minus 2 lots of t equals a1 lots of t plus 2 times a2. And similarly for the second equation. So by splitting up these two equations into equations that match constants and match the t terms, I now have 4 equations for the 4 unknowns. So that means I can solve for a1, a2, b1, and b2 exactly. Okay, so, well, what does that mean? Well, it means that now I can, how am I going to solve this? Well, I can rearrange, for example, this third equation here to make a1 the subject of the equation. So a1 is going to be equal to negative 2 minus 2 times a2. I can use that value of a1 in this last equation, and I'll be able to find the value of a2. I can then use the value of a2 and a1 in these top two equations and find the value of b1 and b2. So if you go through and try to find those values, a1, a2, b1, and b2, what you should find is, well, in fact, actually, b1 and b2 are swapped here, so actually this should be the right solution. You find that a1 equals 3, a2 equals minus 5 halves, b1 equals negative 11 over 4, and b2 equals 23 over 8. So please go through and try to solve the system of 4 equations yourself. Check if you get the same solution as I do. Okay, then I can use these constants here in my definition of xp. So a1 times t, 3 times t, minus, well, plus b1, but b1 is negative 11 over 4, so negative 11 over 4, and similarly for the second line. So I found my particular solution here. And again, recall that the general solution to this ODE is the sum of the complementary and the particular solutions. So therefore, my general solution is as so. The complementary solution here in brackets plus the particular solution. And again, this is not an initial value problem, so I cannot find the values of C1 and C2. They're just some constant. So here I have a two-parameter family of solutions. Okay, the final example for today, we'll look at a non-homogeneous term which involves sines and cosines. So again, the first thing we should do is find the complementary solution, which means solving the homogeneous version of this equation. So finding the eigenvalues of this coefficient matrix A here, well, because it's upper triangular, I can already see that the two eigenvalues are equal to 2. So lambda 2 equals 2, multiplicity 2. Let's find the eigenvectors by solving A minus lambda I, where lambda is 2, times the eigenvector equals the 0 vector. So if I do that, I'm subtracting 2 from the diagonals, so 0, 1, 0, 0. 0, 1, 0, 0 times k equals 0, 0. Okay, well, I can read off now. 0 times k1 plus 1 times k2 equals 0 tells me that k2 equals 0. I have no restriction on k1, so let's just set that equal to 1. So unfortunately, I have an eigenvalue of multiplicity 2, but I only have one eigenvector here, so I need a second eigenvector. So what I'm going to do is I'm going to solve this similar equation. A minus lambda I times k2 now, we're trying to find k2, equals, instead of the 0 vector, I've got k1. Okay, so if I write that equation out, now I have 0 times k1 plus 1 times k2 equals 1 now. Or in other words, k2 equals 1. K1 can be anything, so let's just set it equal to 0. And therefore, my complementary solution is as like so. So you may like to refer back to the case 2 summary slide to make sure that you understand how I got this complementary solution here. Okay, but what I'm more interested in this problem is finding the particular solution. So because my non-homogeneous vector here is a sine and a cosine, I'm going to take a particular solution of this form. A1 times cosine t plus b1 times sine of t, a2 times cosine t plus b2 times sine of t. And again, for each term, even though the first entry in f is just sine, I still have to include these cosine terms. Okay. So now I need, because I want to use this solution in my ODE, my non-homogeneous ODE, I need to calculate the derivative of xp. But that's pretty easy because the derivative of cosine t is just minus sine of t, and the derivative of sine of t is just positive cosine of t. Okay, so now I can use these two vectors in my ODE. Xp prime equals a times xp plus f. So this left-hand side here is xp prime equals a times x, the vector xp, plus the non-homogeneous vector f. Okay, so again, I have somewhat of a problem here because I've got 4 unknowns, a1, a2, b1, and b2, but I need 2 equations. But again, I can play the same game here, and I can separate these 2 equations into the sine and the cosine terms. So for example, here, the cosine terms in the first line, or the first equation, are going to be b1, lots of cosine on the left-hand side, equals 2 times A1, cosine terms here, plus 1 times A2 plus 0. There's no cosine terms in the non-homogeneous first entry. And then similarly, the cosine terms in the second equation are going to be B2 cosine equals 0 times the first line plus 2 times A2 here, plus 1 cosine here. So I can write two equations which relate to the cosine terms and similarly for the sine terms. So now I have 4 equations for my 4 unknowns which I can solve exactly. I do get a nice bonus here because I can immediately see from this last equation that A2 is equal to negative 2 times B2, which I can use in the second equation to find the value of B2. And if you go through, these should be the values that you find for A1, A2, B1 and B2. You might like to check that that is what you get as well. And I can use those in the XP, my particular solution, my test particular solution. So just substituting in the numbers A1, B1, A2 and B2. And of course my general solution to this system of non-homogeneous linear ODEs is just the sum of the complementary solution in brackets here and the particular solution. Okay, so the point is that we can use the method of undetermined coefficients to solve non-homogeneous systems of linear ODEs. So please work through these examples that I've gone through in class and make sure that you are happy with how we solve them. Do some questions from the textbook and the study guide. And again, as always, if you have any problems, let me know and I'd be happy to answer any questions you have. Thank you.